Excellent. So my talk today is about what practitioners need to know about lead in water. I am a researcher, I'm not a practitioner, so I asked my colleagues in North Carolina and Virginia what they wanted to know about lead in water, and these were the 4 topics that they told me about. They wanted to know how to communicate to residents. Where is the lead actually coming from? Because it's not in our groundwater. How do we remediate lead in water problems? And then lastly, how do we sample so we can know how to remediate these problems? So looking at the first one, how do we talk to well users? So I've been working with the Virginia Cooperative Extension, Erin Ling, who you're hearing from tomorrow. And one of the things, Erin and I had the same exact conversation about 2 years ago after our sampling. So we decided we needed an infographic, a 1-page overview to get people motivated about lead in water and testing. So I'm going to walk through what our flyer says. So the first piece is the health consequences. So the sources of lead, when we often talk about them, we think about lead-based paint, lead in soil, lead in dust, and those are kind of our primary sources of lead. But really there's this new transition to talk more about the secondary sources of exposure, things like drinking water. Especially as we continue to remediate lead-based paint, that these secondary sources are becoming more of a significant contribution to our total lead exposure. But really, from a public health standpoint, there is no safe level of exposure. It causes mental and physical developmental issues. And even at previously believed safe levels, we're now finding that there are issues with IQ and other adverse health effects. So really, there is no safe level. So the next is, what is the prevalence? So this is a statistic. We found that about 1 in 7 wells tested from North Carolina, Pennsylvania, and Virginia had lead above the EPA action level. So I'm going to talk about Virginia. So during a campaign with Erin, we were able to sample over 2,000 wells between 2012 and 2013. What we did was we followed the EPA's lead and copper rule. We let the water sit for a minimum of 6 hours, and then we took the first draw of water. We then compared that concentration to the EPA action level of 15 micrograms per liter, and used that as a threshold because we were sampling one sample from each well. So this is our distribution from Virginia. Along the x-axis are concentrations, along the y-axis is our population proportion. So right away, we use a detection level of 1 part per billion in Virginia. What we found was 80% of our well users had detectable lead in water. Looking at the EPA threshold of 15, we found that about 1 in 5 wells in Virginia are actually above that elevated level. Our concentration high was just over 25,000 parts per billion. So this is telling us that we have issues with low levels of lead, but we also have some extreme cases of corrosion occurring. To put this another way, a lot of us have been talking about lead in well water because of the Flint water crisis. So how does wells compare to what happened during Flint? Distribution is the same. We have the same lead and water concentrations occurring in our private wells during routine sampling efforts as we did at the height of the Flint water crisis. So one is clearly capable of impacting public health, and one really hasn't been studied. So this is why we feel that this is a really important topic that we should talk about with well owners. So moving on, where is the lead actually coming from? Looking at our plumbing components and the concept of corrosive water. So lead has and continues to be a common additive in our plumbing components. Now in private wells, we don't have lead service lines, which is the most concentrated source for municipal systems, but we do have other sources of leaded and lead-free plumbing components that can release lead, things like solder, brass fittings, and galvanized iron pipes. So what happens is, when you put these plumbing components in contact with water, during periods of stagnation, you can get chemical redox reactions occurring, and the lead will dissolve, it will leach into the water. This is known as dissolved lead. This is traditional knowledge of where more stagnation period, the higher the lead concentration. But the research is now shifting to have conversation about what happens during periods of water use. Because you can get pieces of pipe, pieces of scale breaking off. You can get leaded sediment that had settled overnight, can get remobilized. It's what we call particulate lead. It's highly sporadic, It's variable. We don't know how to predict it because it's all based on hydraulic disturbances. So this concept of lead-free. Unfortunately, lead-free does not mean lead-free. Lead-free means a legal amount of lead. And this has proven problematic for wells because until 2014, lead-free plumbing components could contain up to 8% lead by weight. So sometimes we'd see that lead was actually concentrated on the surface. So in our lab, what we did was we took these lead-free plumbing components and we redid the certification protocol, and we used their test water, which had a pH of 8 and an alkalinity of 500, which we thought was unrealistic for our wells in Virginia. So what we did was we dropped the pH and we dropped the alkalinity. We made the water more corrosive. So as the water became more corrosive, we got more lead releasing from these lead-free plumbing components. And really what we found was once we started to get around a pH of 6, that we were starting to get too much lead being released from these plumbing components, that they wouldn't be able to be certified as lead-free, that there's too much lead coming out. Fortunately, in 2014, the new plumbing components came out on the market. The Reduction of Lead in Drinking Water Act redefined that lead-free to now a weighted average of 0.25%. So there is still lead in our plumbing, but now it's not releasing to water like it did before because we've significantly reduced the amount of lead allowable. So the other problem that our group is really starting to investigate more is this galvanized iron. So galvanized iron is an iron pipe with a lead zinc coating that's supposed to be protective, that's supposed to corrode before the iron pipe. So when we ran our corrosion test, what we found was that this zinc coating was releasing. As the water became more corrosive, we saw more zinc releasing to water. What's interesting was we found the opposite thing occurring with lead. As the water became more corrosive, we had less lead in the water releasing. And what we ended up finding was that's because the surface was corroding, but that lead was then rebinding with the underlying iron pipe. And so rather than being dissolved and going up to the tap, now it was becoming scales and it was becoming a particulate lead issue, that when you started to use that water and that piece broke off, now you've got a dose of lead, a dose of particulate lead. So now moving to things that are more tangible for homeowners. Where you live, if you have staining issues, we wanted to make it a little bit more realistic for the homeowner. So the first thing is where you live affects what you drink, looking at groundwater and geology. So last summer, the USGS put out a corrosivity map of homeowners, well users that are potentially at risk for lead in water based on different corrosion indices. And so you can see along the East Coast, they have higher potential for more corrosive groundwater. And as a result, if you watched any of the news, different states started saying that they were at risk and really started to encouraging homeowners to participate in lead testing. So this is great, using where you live to communicate the importance of testing. The other piece of this, though, is there were many states that didn't have corrosive groundwater based on this indice, is that you need to talk about what type of system you have, because that's also going to be a very important variable. So I'm going to talk specifically about Virginia. Virginia is one of those states that was noted as having a high potential for corrosive groundwater. Virginia, we actually have 3 geologies. We have our coastal plain sand aquifer. We have our Piedmont Blue Ridge region with a crystalline igneous metamorphic bedrock, and then our carbonate geology in the Ridge and Valley region. So amongst our state, we have different levels of corrosive water potential. And so what we found was when we broke down specific geologies, got a little bit more finer detail, we found that the Blue Ridge and Piedmont was at highest risk for lead in water. And this was really due to the fact that they had corrosive groundwater because their bedrock didn't interact, so there was no buffering capacity of the geology. So I remember talking to Aaron and saying, well, look at this. We don't really need to be worried about the coastal plain because they have the lowest rate of lead. Like, we really should focus all of our efforts on the western part of the state. But then we got to talking, and if you start to consider the type of system, well, the coastal plain does have lower levels, but only for drilled wells. The drilled wells that have higher pH have non-aggressive water. But if you start talking about shallow wells, our bored wells, Well, they also have more corrosive water because there's not as much travel time. So there's not as much interaction between the infiltration and the geology. So it has lower pH water, which means they tend to have higher levels of lead. So it's really important to consider the geology as well as the system type. And then the other thing I'd like to talk about is describe your water. People love to talk about their water. The bigger the word, the more often Aaron and I saw that homeowners describe. So we actually saw more people describing staining problems with their water, typically lime scale, rust staining. And this is really interesting, but we wanted to use it to our benefit, to say if you describe this characteristic, you would be more or less likely to have lead in your water, to use those aesthetic characteristics. So what we ended up finding was we took all of our characteristics, I think we had about 30 of them, and we found 3. We found homeowners who had obvious signs of corrosion. They had plumbing failures, they had pinhole leaks, homeowners who described their water as having a metallic taste, and homeowners who saw blue-green staining. These homeowners were more likely, 1 to 3 times more likely to have lead in their well water than homeowners who didn't have these characteristics. Now, the EPA says you can't see, taste, smell lead in well water or water, but what it is that lead is so highly correlated with copper concentrations with having a low pH that we can use this set of characteristics with pH and copper to communicate lead in well water. So at the end of this, though, we thought it was really important that despite all of this information we give to you and tell you your probability, really the best way to know if you have lead in your water is you have to test your water. So we end by closing and saying, please go contact Aaron and participate in testing. So the next piece is more about what we can do from the technical side. Where is the lead actually coming from? So we talk about municipal systems, we talk about the home plumbing, the premise plumbing. But when we talk about wells, we have to talk about the premise plumbing in addition to the well construction, the well components, because although we do not have pure lead pipes in most of our systems, we do have these traditional leaded and lead-free fittings throughout the entire network. So what my team wanted to do was we wanted to identify where the lead was coming from, look at the patterns of corrosion. So what we did was we'd go into different homes and we'd visually inspect the plumbing network. We'd go into the kitchen tap, look at what fittings were there, we'd go to the wellhead, look at the casing material, and we'd estimate the different volumes of water that would be stored in the different sections of the plumbing network. And then what we do is we take a series of sequential and flush samples. And this was really powerful because we could tell what water sample was coming from where and what component was associated with that piece of plumbing. What water sample was associated with that piece of plumbing. So basically, if we looked at the first draw, which is about 250 milliliters of water, we could say that was 8 feet of plumbing. The next 3 feet, or next 3 liters were the premise, and then beyond that was the pressure tank or treatment or in the well. So the first pattern that we saw was really consistent with our traditional knowledge and what we see in municipal system, in that once you flush the system, the lead is gone. And really it's telling us that we're seeing corrosion at our outlet. There's a lot of brass fittings in our kitchen faucets and at our kitchen faucets. And typically, once you flush, that goes away. The problem is, and this is a new conversation we're seeing in municipal systems, is that with continued water use, you can get these random spikes in lead. And so we saw 2 homes in our study where we had no problem in the first draw, but as we used the water, we had high hits in lead, and it was all particulate. The first home we saw, it was an issue with lead solder breaking off. The next home was associated with corrosion of a brass fitting and scale associated with that breaking off. So those 2 patterns were really consistent with what we know about corrosion in municipal systems. But we ended up finding a 3rd pattern, and this one was unique to private wells. And basically, we flushed some of these wells for more than 45 minutes and still had detectable levels of lead. And what we found was that when we looked at the form of lead, it was all in that dissolved form. So we knew it was all stagnant well water that we were still collecting even after 45 minutes. So basically, this is telling us that components such as the pitless adapter, our check valves, our brass pumps, maybe our casing material, that can dissolve during those periods of stagnation, and it takes a substantial amount of time for us to actually flush out if the well is corroding. So we were really curious to investigate this concept that our source water could be contaminated even before entering the home. So we worked with a county in North Carolina, Macon County, and they've been having issues with corrosion in the well. They had about 14% of their homeowners having high lead when they were collecting specifically at the wellhead. So North Carolina has a code where they require a tap, so we also were going to use that tap to isolate, so we had no influence from the premise plumbing to look at what's going on in the wells. We collected 8 samples. We did, again, a series of sequential and then flush samples, knowing the plumbing network so we could identify where each water sample is coming from. And what we found was, again, we found that concept that once you start flushing, the lead goes away. And so it's associated with our well plumbing. But what was really interesting, it wasn't dissolved lead. It was all particulate. And so what we think is happening is, if we start looking at these wellhead components, we have a ton of brass fittings, galvanized iron components, that they are corroding during these periods of stagnation. Scales are forming, and that when that pump first kicks on, all of that scale that has built up has to clean itself. It has to scour and become clean, and we see these slugs coming through our system until the water is running, getting rid of all that scale. What's interesting was, again, we saw this another second type where we saw random spikes in lead again, where at 5, 10, 15 minutes, we just get 1 or 2 hits. What was really interesting was we had one homeowner who had no lead in his plumbing system, and every single sample had actually contained lead, high levels of lead, around 5 parts per billion. And what we found was, over the years, all of his plumbing had corroded, and now there was a lead sludge, a sediment on the bottom of his well. So anytime the water drew down low enough, all of that sediment was getting mobilized. So every time the well engaged, he would get hits in lead. So really, for these patterns, what we're seeing is there's premise plumbing corrosion. We're having issues with particulate lead, which is consistent with what conversations are going in municipal systems. But the problem is, we have to consider what's occurring in the well. And this is where private wells start to deviate from municipal systems, because we have to be concerned with our source water. And really, this is ultimately important because you can't talk about remediation until you understand where the lead is coming from. So that leads to the next part, is how do we actually start remediating the lead in these wells? So most common, you'll hear people talk about flushing. Flushing until the water runs cold, anywhere from 30 seconds to 2 minutes, maybe even up to 5 minutes. So looking at the homes that we had profiled, we found that the average time it takes to flush between the kitchen tap to start drawing water from the pressure tank was about 15 seconds, maybe as high as 45 for homes that are a little bit bigger. So this is really good. If you have issues with premise plumbing corrosion, flushing is a great option because it removes all of that stagnant water. The problem is, if you have homeowners that have corrosion occurring in the well, this won't work because you're not going to be able to flush long enough to remove all of the contamination associated with that corrosion. So the second option we talk about are point of entry devices to control corrosion, something like an acid neutralizer. So this is a great option, again, if you have premise plumbing corrosion, because it will help to inhibit the corrosion. It will modify the water chemistry to make the lead not want to dissolve. And it will also protect your plumbing in your home, which can be expensive repairs if it starts corroding. But again, these treatment units, these point of entry treatment units, don't consider corrosion in the well. And so any background concentration will not be removed through this point of entry unless it's filtered. And if you have a corrosion occurring in your well, the lifespan of these wells will be reduced, and they will not last as long as if you don't have corrosion. So the other treatment option is doing something point of use, something like an RO or an activated carbon filter. So these are great. From a public health standpoint, you are filtering the water before it is consumed. So they will remove the lead, and the water will be lead-free. The problem is, these don't consider corrosion. in the system. So you may get corrosion, pitting and plumbing leaks in your home or in your well. And then the last option we always have is just to rebuild the system, to remove all of our leaded plumbing components in the home and in the well. But as all of us know, that is extremely expensive, especially for low-income homeowners. So this may not be financially practical. But really what I'm getting at is there is no one solution that will work. It's really dependent on the corrosion that's occurring throughout the system, the financial state of the different residents, the maintenance needs, and how much they want to get engaged with different types of treatments. So you may be implementing one option or maybe multiple options. It really just depends on the specific system. So the last thing is, how do we sample for lead in wells? There's a lot of confusion because there are no standardized sampling protocols for wells, and we really haven't had a lot of discussion about lead. So I want to go back to Macon County, where we sampled 15 homes. So when we looked at first draw concentrations in this area, we had 2/3, 10 of our 15 homeowners had high lead in water, as high as just around 2,000 ppb. So there's some serious concerns. In North Carolina, our current protocol says to flush for 5 minutes before sampling for inorganics, which include lead. The problem with this is when we start flushing, we're cleaning the pipes and removing all of that stagnant water. So when we look at our 5-minute flush samples, most samples now have non-detectable levels of lead, and none would trigger action because none are over the action level. So that act of flushing is reducing our lead in water and potentially missing the exposure. So really moving forward, what our group is recommending is to keep with the lead and copper rule and saying that let your water sit for a minimum of 6 hours and collect that first draw of water. We recommended 250, you can do 1 liter. This is really meant to identify lead in water hazards. If your organization has the opportunity to collect a second sample, collecting a flush sample will be able to help you identify whether you're dealing with premise plumbing corrosion or if there's corrosion occurring in the well, and will really help you identify what type of remediation actions are necessary. As always, from a public health perspective, we recommend collecting waters at a drinking water outlet, but we always know that is not always possible, but if you can, where people are drinking so you can understand what's going into their body. So with that, I just want to acknowledge my numerous supporters and colleagues and collaborators and say thank you. I told you I'd be short.
Questions for Kelsey?
Hi, Kelsey. I have a question.
Yes.
Does any of your research in looking at premise plumbing suggest a timeline when homeowners in the future, if they have premise plumbing that's aging out essentially, where it's going to start to affect their water quality, would be advised to do something about that in order to avoid slugs or particulates on a regular basis? Has there been any research around the time, given we have many wells, I'm sure, that are very old?
We haven't looked. That's one of the things we're looking right now in North Carolina is they use a lot of galvanized iron, so we get a lot of that scale forming on the iron pipe. We haven't looked at how quickly that galvanized surface actually corrodes. So I don't think anyone's really looked at that. As for aging of systems, I mean, pinhole leaks, if you get localized corrosion, something that's occurring not all across the system, they're going to pit out a lot quicker, but some of these components can last, 50 to 100 years, so that's not going to be an immediate action for people because it's not, unless you have a very old home, it's not going to be a concern necessarily.
Just quickly share, we did a study, actually it was about manganese, which I don't think is on the agenda, but we should probably talk about manganese sometime in next year, Steve. But we also sampled for lead and in partnership with the county. And we had a system, they were sampling from an outdoor tap, which was a galvanizer, maybe a copper spigot. But they would flush the well, flush for a long time, where the parameters were, stabilized, and we just wanted to test the well water. And they'd shut the thing off, go get their sample bottle, turn it on. And so the physical action of the turning of the valve, even if they let it run for a second or two, there was this big high lead concentration we didn't expect. And so when it comes from a public health standpoint, you turn the tap on, maybe you don't let it run. So that's still a concern, but it was that physical turning of the valve. And I'm wondering if that's something you addressed too.
Yeah, so that's why it's tough with private wells. So for example, in North Carolina, our wells are constructed and sampled sometimes before the home is actually constructed, so we don't have a kitchen tap. So looking at those outdoor spigots, they might not be rated for drinking water, so they might actually contain more lead than you would normally see in a drinking water outlet, so that can skew results. The other thing is absolutely is the turning mechanism. You're turning metal on metal, you're going to have issues. And then you also have to think these taps are not being used that often. We sample maybe once a year if we're lucky, every 5 years or so. And so you can get those taps can sit with long periods of stagnation, allowing more and more corrosion to occur or junk to build up. So they can be very biased. That's why, again, if you're really concerned from a public health standpoint, we recommend going to a tap that's used frequently for drinking water. But yeah, that absolutely is occurring.
The material that was at the bottom of the well that you found some lead, was that associated with an older well or
No.
certain type of equipment? Okay.
So what we've been seeing is, so in North Carolina, you have 30 days to test your sample or test your well after it's constructed. So the wells we were targeting had been, I think the oldest one I had was like 2005. So I mean, it depends on what you call old. But really it's the galvanized iron is causing, galvanized iron casing and then galvanized iron drop pipe that's causing these sludge layers to build up. Obviously, the longer it's been in use, the larger the layer is. But I know that some of our county health officials are right now cleaning that out, and that's really helping to remediate some of the lead problems once they start removing that sludge on the bottom. Or if that's not an option, lifting the pump up higher so it doesn't mobilize that lead.
Thank you very much.
Thank you.